Okay, hello everyone. Those of you who are logged on and those of you who are going to be watching later. I have the practice final here set up. I'm going to go through starting with the actual question parts, so not the fill in the blanks there. If you have any questions on those, let me know. But we're going to start here. For sure, there's going to be lots of limit questions. So graphically finding limits and finding limits with just, the functions. So we have some examples of limits with graphs. The first one here, finding the limit as x goes to 0 of the function. So remember, one thing that always has to be true for limits is that in order for a limit to exist, the left side and the right side of the limits have to be equal. So what we want to do is, if we want to find the limit as x goes to 0, we have to check limits from both sides and make sure that they're meeting the same y value. The y value doesn't have to exist, but they have to meet at that same location for the y value, which in this case is 4, so the answer would be 4, since the left and the right side meet at y equal to 4. Number 2 is specifically checking to see if you can find left and right side limits. So the limit is x goes to 6 from the left side. That means we have to first find where x is equal to 6. So we see right here, this is where, I wanted to do that. This is where x is equal to 6, and we want to find the limit as x approaches 6 from the left side. That's what that minus means. So from the left side, we follow this path of the function from the left, and we see that it reaches a y value of -4. So then our answer would be -4 in this case. If it was just asking you for the limit as x goes to 6 of f of x, that would mean you have to check both the left and the right side, and we would see that the left goes to -4, the right side goes to -1, so this limit does not exist. We have that jump discontinuity there. So it can't exist because the left does not equal the right. And number 3, if the limit as x goes to 2 is equal to 3, what is the value of the limit as x goes to 2 of 4 times f of x? I think we went over this in class already. It's just checking your limit properties. So limit properties mean that you can break apart different parts of limits. So for example, here, we can break this apart to the limit as x goes to 2 of 4 times the limit as x goes to 2 of f of x. It's almost kind of like distributing that limit. You can think of it that way. So the properties say that you can actually do that, which means the limit of any number is just the number itself, so that would be 4. And then they told us that this limit is equal to 3. So you just end up with 4 times 3, which is 12. So that's what you want to do with these kinds of properties. It may be addition, maybe subtraction, but it's still that same idea. You can kind of distribute this limit and take the limit of each thing separately and then combine them once you find the limits. All right, number 4, we plug in -2, and we already see right down there, when you plug that in, we get a denominator of 0. So we have to use our limit methods to somehow fix this. The best option I see here is we're going to need to factor. So this is equal to the limit as x goes to -2. Remember, you always have to rewrite that until you actually find the limit. And then we are going to factor this. So 2x and x. 2 breaks down into 2 and 1. We want it to be a +3, so this has got to be positive and negative. All over x plus 2. That's what we want to see. We want to see things cancel because now we're finding the limit as x goes to -2 of 2x minus 1. And direct substitution, plug in that -2. We get -4 minus 1 is -5. So these kinds of problems are really interesting because you can get used to just doing the calculations, but really it's important to stop and think sometimes, what does this problem really mean? What does it mean when I'm crossing out that factor? It means that we have a whole at x plus 2. But remember, in that first example, I'm going to scroll up here, right over here, remember we had a whole, but the limit still existed. It still was there. We could find its y location. So that's basically what we're doing, is we're finding where that y location really is in this problem here. By canceling out that whole, it leaves us with the actual equation for that function where the whole exists. And so we're locating that y value by getting rid of that whole. So something to keep in mind. Make sure if you want me to skip ahead to anything that you really want me to get to, either in this or also I have the other practice packets downloaded here. So I have this one, packet number 2, and packet number 1. If you have any questions, just type it in the comments. Let me know which packet you want me to do answer a question from. So number 5, evaluate the limit. So again, we always want to try direct substitution. When I plug in a 4, surprise, surprise, we're going to get a 0 in the denominator. So I know that I'm going to have to rationalize. How do I know that? Well, there's a root. So the way that I do this, I'm going to multiply by the conjugate, which is going to be root x plus 2. Remember, everything stays the same except for the sign that separates the two terms. That becomes opposite. So I multiply the top and the bottom by that term, or by that expression there. So in the top, I'm not going to distribute anything. I'm not going to really mess with it. I'm just going to write those two factors there. Down in the denominator, this is going to multiply to x minus 4. Root x times root x is positive x. Negative 2 times 2 is negative 4. So that's what we get there. Oops. Those are going to cancel. So once those cancel, I'm left with the limit as x goes to 4 of root x plus 2. And that's going to equal, when I do direct substitution, root 4 plus 2, which is equal to 4. So again, another tip and something that I want you to kind of get used to doing, even as we go into the next semester, is kind of stop and think of the calculations that you just did and what they really are representing, because it can be really easy to get into the habit of just doing the techniques, but really I want to make sure that you're thinking about what is happening when we are multiplying these out, when we are canceling out these terms. So this is another situation where we had a whole and we had to cancel out that whole, and we're left with a function here. So this was a square root of x function moved up 2, and it has a hole in it. This one here was a line, 2x minus 1, so a line like this, and that line had a hole in it. So that's kind of, I want you to make sure you're thinking about what is it that I'm finding when you're doing these problems. Number 6, the limit as x goes to 7 from the right of the absolute value of x minus 7 over x plus 3 times x minus 7. You bet there's going to be a problem similar to this. We've been doing absolute value of limits in your bell ringers all this semester, so you should all be pros at it, but we're going to go over it again. So when I plug in a 7, because remember, even though it has that right side here, if we're calculating limits, you always just want to do direct substitution first and then see if you get an answer, because if you get an answer once you do that direct substitution, then that's it. You don't have to do any more work. But when I do plug in 7, I get 7 minus 7, which is 0. So now I know that I need to do some extra work here. And that's going to direct you right to this absolute value function, because that function is actually two functions combining to give you one function. And so here we're looking for the limit as x goes to 7 from the right, which means that we only want one part of the function. X minus 7 is an absolute value function where we are shifting it over to the right 7, and it looks something like this. So if you look here, the little v, the corner is right at 7. So that means on the right side of 7 here, this is an equation of a line that's a line with a positive slope, so that's just x minus 7. On the other side here, this is an equation of a line that has a negative slope, so it becomes negative x minus 7. So keep that in mind. If we're finding the limit as x goes to 7 from the right side of 7, well, the right side of 7 is all of this side. And what is the equation for that side? It's x minus 7. So that means that I'm going to rewrite that function there. The limit as x goes to 7 from the right. I'm going to rewrite it as this function. So x minus 7 over x plus 3 times x minus 7. Because that way the solution, the y value that I get from here is going to match up with what I'm looking for. And these are going to cancel, leaving me with the limit as x goes to 7 from the right, 1 over x plus 3. And I can just do direct substitution once those canceled, and that gives me 1 over 10. So that would be my solution there. So always think about what are the two functions that make up the absolute value? Like we see here, there's always going to be the positive, and then there's always going to be the negative. And then decide, what is the question asking you to look at? Is it asking you to look at the right side, or is it asking you to look at the left side? And that'll direct you to what you need to replace that with. Okay, number 7, this limit will come up for sure. We should know that the limit as x goes to 0 of sine x over x equals 1. And then if we have anything other than x, we should have the same thing down in the denominator. So in order to get a 2x in the denominator, I have to multiply it by 2. But whatever I do to the bottom has to happen to the top. So this is getting me the limit as x goes to 0 of 2 sine 2x over 2x. And I see there's a question here. If it asks from the left, what equation would we plug in? So if this problem here was saying find the limit as x goes to 7 from the left side of 7, well, you want to think about the absolute value function that's created here. So the right side of 7 is the function x minus 7. The left side of 7 is the function negative x minus 7. So that would be the function that you want to use. So this would be rewritten as the limit as x goes to 7 from the left of negative x minus 7 over x plus 3 times x minus 7. So then those are going to cancel out, leaving you with a negative 1 over x plus 3, which I'll plug in the 7. And that'll give me negative 1 over 10. So that's what you would do if it was the left side. So always think about breaking down the absolute value function. So absolute value of x is equal to x when x is greater than 0, negative x when x is less than 0. So depending on what you have plugged in, that's going to change this value, and then you'll just have that match up. So if it was something like x plus 2, this would become positive x plus 2, and this is x greater than negative 2, and this would become negative x plus 2 when x is less than negative 2. And how do I figure out what this number is? You set this inside equal to 0 and solve for x. So that's what you would do for any absolute value function. Always figure out what the breakdown of it is, and then these conditions will help you decide if it's the left side or if it's the right side of that number. Okay. So hopefully that answered that question for you. Let me know if you have any other questions on that. So back to number 7, we wanted to get, since we had a 2x plugged into sine, we wanted to get a 2x down here, which now we got. So this part right here, and this is kind of where your limit properties, why we learned the limit properties to begin with, is basically saying we want to take the limit as x goes to 0 of 2 times the limit as x goes to 0 of sine 2x over 2x, which, based on our rule here that we already learned and has been proven for us, we know that this part is going to equal 1, and then the limit of any number is the number itself, so then that just becomes 2. It's easy to just see that there, that's going to become 1, and so then you're left with a 2. But this is kind of showing you the proof of it here, and also just kind of showing you why we learned the limit properties to begin with and why we're kind of tested on those properties as well, because you're using it without really even thinking about it sometimes. And so the answer is 2, in case that wasn't clear there. Okay. Number 8. So keep in mind this part right here. Whenever you're looking for the limit as x goes to either positive or negative infinity, this is actually telling you what the horizontal asymptote is of the function, or it's what you're finding when you find the limit. Because if you think about it, the horizontal asymptote is the y value as these x's are all going to positive infinity or as they're going to negative infinity. So always keep in mind when you're finding that limit as x goes to infinity, that's what you're finding is a horizontal asymptote. And we need our rules. So whenever this is infinity, we need to think top heavy, bottom heavy, or same degree. And so we see here, this is a third degree on the top, second degree at the bottom. So this is a top heavy function. If it's top heavy, we know our answer is going to be either positive infinity or negative infinity. So the way to check that, we look at, first of all, is it positive or negative infinity? In this case, it's negative infinity. So I'm going to think about what happens when I plug in a negative here and a negative there. And when I do that in the top, negative cubed stays negative, times a negative 4 becomes a positive. And then I plug in a negative down here, negative squared becomes positive, times this negative is a negative. Positive divided by negative gives me a negative. So my answer is going to be negative infinity. I knew it was going to be infinity or negative infinity because it was top heavy. And when I check to see what happens when I plug in a negative value, I see that it's going to negative infinity. Remember, if it's bottom heavy, the answer is going to be 0. You're going to have a horizontal asymptote at 0. And if it's the same degree on the top and bottom, then you are going to look at the ratio of the coefficients there. Okay, number 9, we have a lot of vertical asymptotes here, and we're specifically looking at what's happening when x is approaching 4. So I'm going to zoom in here to where x is equal to 4. I see that there's a vertical asymptote, so most likely it does not exist if they're going in different directions, but I see that on the left side of 4, on the left side of 4, all these y values are going to negative infinity, and on the right side of 4, these y values are still also going to negative infinity. So the left side is still equal to the right side in this case, so that means that the total limit is going to be negative infinity in this case. So that would be our limit as x approaches 4, because we had to check both the left and the right side. If, let's say, the right side was going up like this instead, and the left was going down, then the limit would be neither. It would not exist because they're going in opposite directions. But since they're going in the same direction, then our limit is that negative infinity there. Okay. So the limit as x goes to negative 2 of x plus 1 over x plus 2 to the 6th power. If I plug in a negative 2 here, I'm going to get a 0 in the denominator. So I got to come up with some other way of solving this. Factoring is not going to work. Rationalizing is not going to work. I don't really see anything else that I could do to make this work. So this means that we're left with a non-removable discontinuity, which is a vertical asymptote. Remember, your non-removable discontinuities are vertical asymptotes and horizontal asymptotes, which we saw up here how to find these horizontal asymptotes. Here, vertical asymptotes, you're always going to have a number there, and when you plug into the denominator, it's going to give you a 0. So what we want to do is we want to figure out, just like what we saw here, what is happening to the left and the right of the limit, and we want to see, are the y values negative or are the y values positive on that side. We did this example in class, I believe, and so remember we plug in something to the left of the value. So let's say if we plug in a limit as x goes to negative 2 from the left, would mean we'll plug in something like negative 3. So I have this function here, plug in negative 3, oops, I did not mean to write a 3 there. That's going to be negative 3 plus 2 to the 6. This is going to give us negative 2 over a positive 1, because this is an even degree, gives us a negative value. So this is telling me, kind of like this example here, that on the left side, since I got a negative y value, all of the other y values are going to be negative. So it's going down towards negative infinity on the left side. Now on the right side, I'm going to think of a number to the right of negative 2, for example, negative 1. When I plug that in, already I can see that when I plug this in, sorry, my notation is bad. I should have rewritten the function here again. this part should be rewritten right there. And I already see that's going to give me a 0. So that's not telling me anything. That's kind of like, if you see this example here, it's like plugging in a number to the right of 8 and then getting this. So it could be going up to positive infinity, but it could also be going down. So we need to plug in a number that is still to the right of -2, but not -1. And we don't want to go too far away. So I'm going to try -1.5 because that's still close enough. Remember, we did this in class, so hopefully it's still kind of fresh in your mind how to do this. It's going to give me a -0.5 on the top. What do I get here? A positive value at the bottom. So negative divided by positive is going to give me a negative. So this is telling me that on the left side, it's negative infinity. The right side, it's also going to negative infinity. It's kind of another like situation from what we saw here with the 4. So our limit is going to be negative infinity because of that vertical asymptote there. So we have vertical asymptotes when none of our other techniques work. Remember, here we said this was a whole because that canceled. This was another whole because that canceled. So the techniques worked in these examples. Over here, they don't work because we just have a vertical asymptote. Okay. I keep repeating that, but these are really important concepts that I want to make sure that you understand those. That's kind of the essence of this semester, is making sure that we understand these aspects of limits and then derivatives, which we're going to get into right now. So this is naming the function. Our function is h of x equal to f of x times g of x, and we want to find h prime of 2. So what we need to do is we need to take the derivative of this, and the derivative of two functions that are being multiplied means we're going to use the product rule, and the product rule is the derivative of the first times the second plus the derivative of the second times the first. So that is our product rule. And then if we want to find h prime of 2, we're just going to plug in 2 to all of these parts here, just like this. And once you do that, we are going to look at the table. F prime of 2 is equal to 5, so I can replace that with a 5. G of 2 is equal to -1, so I go ahead and plug that in. G prime of 2 is 2, and then f of 2 is 5. So I will plug that in there. And now we're just simplifying. 5 times -1 is -5 plus 10 equals +5. Okay. These are very popular types of problems, types of AP problems, where they'll define a function. Maybe they'll do h of x is equal to f of g of x. So you would need to apply the chain rule in this case because you have a function within another function. The chain rule says you got to take the derivative of the outside but keep the inside times the derivative of the inside. So this is me applying the product rule, and then you would do the same thing if we're trying to find h prime of 2. Then you would plug in 2 there and 2 there, and then just find the values from the table. So these are very popular. You might see h of x is equal to f of x over g of x. So then you would apply the quotient rule and then plug in whatever value you're looking for. So this is just checking to see, do you know those derivative rules? Can you apply those to just two random functions? Number 12, we want to find the derivative, and this is really a power rule. So we always want to see how can we rewrite a function before we take any derivative. So this is the same thing as x to the 5/4, because this is really x to the 5 to the 1/4. Now we take the derivative of this. It's just a power rule. So this becomes 5/4 x. I take this 5/4, multiply it to the front, so that's where I got that 5/4, and then I need to subtract 1 from the degree there. So 1, I can think of it as 4/4, just to get a common denominator, so that's going to give me 1/4. So my answer is 5/4 x to the 1/4. I can rewrite this. This becomes a 4th root, like that. And that's our answer there. You can write it in the numerator. You can do like a fraction like that if you want. It's going to go in the numerator because it's not a negative 1/4, it's a positive 1/4. But that will be our answer there. Okay. 13. These are always a little bit tricky, so you need to make sure that you know that the derivative of any inverse function is equal to the reciprocal of the derivative of that function. Okay? But now this x value is the x for your inverse function, right? But it's the y value of your f of x, right? So this value here is not the same thing as that x right there. So if we're trying to find the derivative of the inverse at 8, I'm not going to say 1/f prime of 8, because that's not the correct relationship that we have going on there. The correct relationship would be this 8 here is actually your y value. It's actually f of x. So what I need to do is find the x value that goes along with that. So over here, f of x equal to 8 has an x value of 3. So that's actually what's going to go right in here, is the 3 that matches with that. Once you have that set up and that relationship, you got that going on, then all you have to do is look at the table, see what is f prime of 3, and that is equal to 6. So we have 1/6. And that is our derivative in this case. So number 14 is a chain rule. We all love the chain rule. We need to rewrite this before we take any derivative. So 5x is the inside, and we have a power of 1/2 on the outside because this root is covering, or is on the outside of that whole function there, 5x. So that means the 1/2 has to be on the outside of that whole thing. Chain rule tells us we need to take the derivative of the outside. My outside is x to the 1/2. So the derivative of that would be 1/2 x to the negative 1/2. Notice I don't even bother writing x right here in this little part. Well, now I did, but what I want to do is I want to keep the inside that was plugged in, and my inside here is 5x. So that's what I'm going to have there. And then I have to multiply, and everyone always forgets to do this. Do not forget, you got to multiply the derivative of the inside. So we said the inside is 5x, derivative of 5x is 5. So I got to multiply that to my whole entire thing. And since this is all just one big term here, I can see how 1/2 and 5 are going to multiply and give me 5/2. Oh, wait. Don't make that same mistake that I was just about to make. This 5x is inside the negative 1/2, so you can't multiply this 5 to this part here. It's got to stay inside of that root or that power, whatever you want to call it. So this has a negative exponent and a fraction exponent. So I'm going to flip it and turn that back into a square root. So that would be my answer. Put it all in one fraction and simplifies to 5/2 root 5x. That is our lovely chain rule. One example of it. 15 is an even better example of our chain rule. I'm going to shrink this a little so I can have some room. Oops. There we go. Throw it over there. I hope you guys are like pausing as you're watching the video, just in case I'm going pretty quickly. I'm sure you guys are all pros at watching videos on YouTube, so I don't have to tell you how to do that. Anyways, so y is equal to sine squared 4x. So this little guy right here, that 2, is really just a fancy way of writing this. So already I have a chain rule. My outside function is x squared, and my inside function is sine 4x. Well, taking a look at your inside function here, well, the whole thing, but really noticing that this is going to be another chain rule when we have to take the derivative, so we'll take care of that in just a minute, but keep that in mind. This is a double chain. So we have an outside and an inside. We're going to take the derivative of the outside. Derivative of x squared is 2x, but keep the inside. We said the inside is sine 4x. So there we have it. Our derivative was 2x. I replaced the x with sine 4x. Now I need to multiply by the derivative of the inside. So I need to take the derivative of sine 4x. That's going to be another chain rule. My outside, in this case, is sine x. The inside is 4x. So I have to take the derivative of the outside. That's going to be a, why do I have that line there? Derivative of sine is cosine. Keep the inside, so I'm not writing the x, I'm writing 4x in order to keep that inside part, times derivative of the inside. Derivative of 4x is 4. So I'll even put brackets here so you can see how this kind of worked out. This is the derivative of the outside, keeping the inside, and this is the derivative of the inside. And we had to do another chain rule here. This is the derivative of the outside, keeping the inside, times the derivative of the inside. So those are all the different parts. Since this is all just being multiplied all together, I can do 2 times 4 is 8, and sine 4x, cosine 4x. I'm just going to point this out because it may come up in an AP test, and it's just something that I want to have you familiar with, is we do have our trig identities, and one of our identities says that sine 2x is equal to 2 sine x cosine x. So I want you to be thinking about anytime you see sine times cosine, see if it'll work for this identity. And this is one good example where it does work. Even though we have a 4x, as long as both of these are 4x, and then we have this 8 over here, 8 can be broken down into 4 times 2, which gives us that 2 that we know has to be true for this trig identity. So since we have that going on right there, that is going to equal 4 times sine 2x. Well, remember we had 4x there, so this should be 2 times 4x. So this will become 4 times sine 8x. Okay. I don't remember if I happen to put anything like this on your final, but it is something that you should be aware of. You might actually want to put your trig identities on your reference sheet if you think that maybe that would help you. So that's kind of one of my suggestions there. Especially with multiple choice, you want to be able to simplify things in ways that maybe you hadn't thought of, because your answer is there as one of the choices, and you just got to kind of work with what you have. Another good tip that I just came up, or I didn't come up with, but I just remembered, if you have things, I don't know, like let's say you have negative x plus 1, remember that you can rearrange this in different ways. This is the same thing as 1 minus x, right? Or you could even factor out a negative value, and it's the same thing as negative x minus 1. And maybe if you had a negative in the denominator already, you can see how things can get rearranged and they look a little different, but they're actually still equal. So keep that in mind, just little tips there for you to think about when you're working with multiple choice questions. Always try and rearrange the values or the terms that you see there. Okay, so I'm about 47 minutes in already. Sorry I talk so much. Let me know if there's any other questions here that you want me to get to before I sign off in about 10 minutes. I have solutions for these. I'm going to post them. I scanned them and can't really see everything, so I'm going to try scanning it again to make sure that you can see all the solutions. And then let me know if you have any questions on that. Number 6, we want to find the derivative of x to the sine x. So this is a situation where we have to use ln. And how do we know that we have to use it? It's because we have a base that is a variable, and we also have an exponent that has a variable. You can't find any derivatives because we know how to find the derivative. Let's say if it was 2 to the sine x. This would be a chain rule with 2 to the x as your outside function and sine x as your inside function. So that would be something that's fine. But if you have something like this, x to the sine x, it's kind of hard to see what is your outside function and what is your inside function. You just can't really figure that out. So we want to take that function, set it equal to y, and then take ln of both sides. So we're going to have ln of y is equal to ln of x to the sine x. And this is where our ln properties come in. This power gets to come out and multiply right in the front. So this becomes ln y equal to sine x times ln x. And now we can just take the derivative implicitly, so piece by piece. We have the derivative of ln y on this side. It's going to be 1 over y dy dx. On this side, it's a product rule, sine x times ln x. So derivative of the first will be cosine x times the second, plus derivative of the second times the first. And that is our product rule there. Now the next thing that I'm going to do is I need to solve for dy dx, so I'm going to multiply by y to both sides. And I get dy dx is equal to y times cosine x ln x plus sine x, I can put that in the numerator, over x. And final step, y is equal to x to the sine x. So you want to make sure and replace that before you find your solution here, or your derivative here. Sine x over x. Okay, so that's our derivative. Okay, let's see here. Could you go over 25 and 26? Sure. Let's scroll down here. 25, derivative of f of x equal to pi. Remember, pi is a number. 3.14, what is it, 15926? Anyways, derivative of any number is 0, right? Any number. Pi is still a number, so derivative of that is just going to be 0. If I gave you f of x is equal to 25, derivative is going to equal 0, okay? 26, y is equal to e to the 2x times tangent 2x. So when I read this, e to the 2x times tangent 2x, there's two functions there. There's this function and there's that function. So I'm going to start out with the product rule. And product rule says you have to take the derivative of the first function, so derivative e to the 2x. That derivative is going to be a chain rule. So my outside function is e to the x, inside is 2x. Derivative of the outside, I love these e's because it's just e to the x, right? But keep the inside. So we have that, e to the 2x. And then we just have to multiply by the derivative of the inside. So derivative of 2x is 2. I'm just going to throw that right in front to keep it nice and condensed there. So this is our derivative of the first function times the second function, so tangent 2x. Okay, that's the first part of the product rule. Then we have to add the derivative of the second function. Derivative of tangent 2x has to be another chain rule that we do. So our outside function is tangent x. The inside function is 2x. So the derivative of tangent is secant squared x, but keep the inside, which is 2x, times derivative of the inside, is 2. So I'm going to do the same thing. I'm just going to put that 2 in front just to keep it all nice and condensed there. So this is my derivative of tangent 2x, and then times the first function is e to the 2x. So that's it. That's my product rule with those chain rules scattered throughout there. This is all one term. That's another term. So if we're simplifying, I'm going to look to see that they have a 2 and an e to the 2x in common. And that leaves me with just tangent 2x in that first term and secant squared 2x in that second one. And then that, I'll just leave it as my derivative. Okay, so that was a fun one. Let's see here, 17, 19, and 21. Okay. 17, what is the slope of the tangent line of the function f of x? Slope is derivative. So this is just asking us to find the derivative, because the slope of the tangent line, the way we always find that is just taking the derivative and plugging in the x value. So that's all we need to do in this case. It doesn't say what is the equation of the tangent line, so we don't have to use the equation y minus y1 equals m times x minus x1. We don't have to use that because it's not asking for the equation. It's just saying what is the slope of that. So we're just trying to find that m piece. I need to take the derivative of f. That's going to be 12, oops, don't forget the equal sign, 12x to the third plus 6x squared, and then plug in 2. So I'm going to get 2 cubed plus 6 times 2 squared. 2 cubed is 8. 8 times 12 is going to be 96. plus 6 times 4 is 24, and 24 plus 96 equals 120. So that is our slope. That's all we need for number 17. Let's see here, 19. If it did say what is the equation of the tangent line, you would take that 120, of course, plug it in for your m, then plug in your x value here, and then you need to find the y by plugging in that x to your function here. So that would give you your equation, but it was just asking for the slope, so that's all we had to do there. 19. Show the first step in using the definition of the derivative to find f prime of x. So when we first started looking at what the derivative was, we connected it with limits, because that's kind of the other foundation of calculus, is how did we connect those two main concepts. So we got this formula here. That's a minus f of x over h. And this formula, well, this part right here is the slope formula, just rewritten a little differently. And remember, the derivative is the slope. So, and it's your slope as it's approaching some value. So as h approaches 0, that's representing you moving towards that value. So this is an important, very important definition just of calculus in general, and that's what we're using for this problem in order to find the derivative of x squared. So remember, we had to do we did it last year in pre-cal honors, and we started out with it this year where we would take f of x, plug in x plus h into it. So we would get the limit as h goes to 0 of x plus h squared, because our f of x was just x squared, so when you plug in x plus h, that's what you get. And then we go, the next piece says minus f of x. Well, our f of x is x squared, so we got minus x squared over h. H is just a variable. And that variable is what we're taking the limit of normally when we're solving this. That's the first step. That's the equation that you would need for that first step. We practiced a lot of how to actually solve this. Once we learned the derivative rules, it became unnecessary, because now if you were to solve this, you would end up just getting 2x. So remember, we used to do all that work just to solve for that. But yeah, that's the first step. That would be your answer here. The first step of finding the derivative using the definition of the derivative. Let's see, that was number 19. 21. Find the average rate of change. So this is all kind of connected here. So average rate of change, if you have a function, I'm just going to draw a function here, something like this, and you have a point here, let's say this point is A, and this point is B. Whoa, okay, there we go. That's B right there. The average rate is just the slope between those 2 points. And that's also actually what this function there is. That's just the average rate, essentially. So in order to find the average rate, you're just finding the slope between those 2 points. The only thing we have to do here is figure out what those 2 points are. So you can also just kind of memorize this formula if you want to. Average rate of change is f of b minus f of a over b minus a if we're talking about the average rate within the interval from a to b. So if you're kind of looking at this picture that I drew here, This is the interval from a to b. This is f of a because that's the y value, right? This is f of b, or whatever this y value is there. That's your f of b. So to find the slope, it's just, sixth grade stuff. You take your y value, f of b, minus your other y value, f of a, all over b minus a. So those are your x values, right? That's essentially what this formula is. So if we go to what the function is, what do we have here? X squared minus 2x plus 1 on the interval from -1 to 2. So basically the formula says this is my a, this is my b. I'm going to do f of 2 minus f of -1 over 2 minus 1. I'm really literally just plugging into this formula there. And then solving. So f of 2, I'm going to just plug in 2 here, like that. That's going to be 4 minus 4 plus 1 equals 1. So I have a 1 there. Minus f of -1. So I'm just going to plug in -1. It's going to give me -1 squared minus 2 times -1 plus 1. And that's going to be what? 1 plus 2 plus 1 is 4. So I have 1 minus 4 on the top. 2 minus 1 is 1. 1 minus 4 is -3. So my average rate of change is -3. So that's just finding the slope of the line connecting those two values. So for example, if this was the function, I just kind of did a random one, but let's say it was f of x, then the slope of this line is -3. Clearly it's not because this is a positive, but anyways, hopefully you get the idea there. Okay, any other questions here? My iPad is slowly dying and I'm not at home, so I can't charge this, but I guess I'm just going to close it off here. Let me know if you have any other questions. I'm going to post the solutions when I get home soon, and so that way you can kind of look things over. Remember, you are going to have free response questions on the test that you can pick one of 3. These are pretty similar to what you'll see on the test, so make sure you kind of go over these. Take a look here. This is implicit differentiation that you're going to have to do. We did an example that's kind of similar to it already in one of the other problems. This is pretty much like what we did in the last test, looking for maxes and mins and that sort of stuff. And here we're talking about discontinuities, removable discontinuities, vertical asymptotes, horizontal asymptotes. Remember to justify your answer. I posted before in your notes early on in the semester how to justify those 3 specific discontinuities. So make sure you check in your notes for those charts and those justifications, because that's going to be how you want to make sure to justify each of these. Same thing for here. Notice pretty much every single one says justify. So you want to make sure that you are justifying correctly. Interval of f decreasing, you're going to say f is decreasing because f prime of x is negative. So you need to make sure and make that distinction between which functions you're talking about. So f prime of x is telling you what f is doing. Over here, when we're talking about concavity, you're going to say that f is concave up because f double prime of x is positive. So make sure that you are clearly stating that the derivative, whatever derivative it is, it's telling you information about that f function. It's telling you when is f decreasing. It's telling you when is f increasing and all that. next semester we're going to be graphing F. So that's kind of our goal when we get back from the break. And yeah, so I'm going to sign off here, and I'll post the solutions soon. And happy studying. Good luck to all of you on the rest of your finals, and I will see you tomorrow.